Namaste, Dr. S.Balachandra Rao ji, and to all the friends and Yoga Brotherhood who have joined us live on this Rishi Vatika YouTube channel. I am Venkatraghavan, Director, International Institute of Vedic Sciences, IAVS, and the host of this session. Let's start with a prayer. Gurur Brahma, Gurur Vishnu, Guru Devo Maheshwaraha, Guru Sakshat Parabrahma, Tasmai Shri Gurave Namaha. Welcome to Dr. Vedavyas Memorial Online Lecture Series being conducted by International Institute of Vedic Sciences, Rishi Vatika, and promoted by Vedavyasa Bharati Trust, USCAFE, and Yoga Brotherhood of America, with the blessings of our Pujya Guruji, Dr. Vedavyas. Today, we are very fortunate to have Dr. S. Balachandra Rao ji to talk about Indian classical astronomy as the 57th talk in the online lecture series. Before we start today's session, with your kind permission, sir, I would like to introduce the book of our Pujya Guruji, Dr. Vedavyas, titled Science of Time, published in the year 1997. Dr. Vedavyas comes from a family of traditional Vedic scholars and is an author of 100 plus books in English and Telugu languages. In the book, Guruji explains about the cover page of the book as the Wheel of Time of God Lord Vishnu, based on an ancient temple carving of 500 AD, which portrays time as a wheel, ever revolving and destroying, moving always forwards and never turning back. It is a symbol of the zodiac, which we call Rasi Chakra, the cycle of the sun god, the flaming deity of time in the inset. The 6 seasons, Ritus, are symbolized in the 6-pointed star of stellar god of universe, God Vishnu, signifying eternal, endless time, Ananta Kala, as we call it. It is worshipped with Vedic mantras and installed on the high pinnacle dome of all temples in India. This motif picturizes the science of time as ancient and hoary origin of all chronologies from Chaldean, Egyptian, Chinese, Babylonian, and Vedic, conveyed by the zodiac. The same ideal of time is geometrized as the Great Pyramid, called the World Horoscope, and as the Clock of Time. With this, I would like to now introduce our guest speaker of the day. Dr. S. Balachandra Rao has superannuated from his office last year as Honorable Director, Bhavan's Gandhi Center of Science and Human Values. After serving for 15 years, post-retirement from National College as Principal and Professor of Mathematics for 35 years. Currently, he is the member of the International Astronomical Union, IAU, headquartered in Paris. Dr. Balachandra has authored about 30 books, 15 each in English and Kannada, on Indian mathematics and astronomy, and also published several research papers singly and jointly in national and international journals. So now I would request Dr. Balachandra ji to shower his blessings through this talk. Over to you, sir.
Start with Friends, good morning to you all. In my today's talk, I try to present some glimpses of the development of astronomy during ancient and medieval periods. Of course, I may rarely refer to the recent developments in our modern astronomy, though our Indian astronomers who are currently working have also made a great mark in the arena in the development of astronomy, astrophysics, and space science. But I confine myself to what India did right from the Vedic period up to, say, the Kerala period of about 18th or 19th century, before the British education system was introduced in this country. So without further much introduction, I will try to present the slides, because within the restricted time, it may be difficult to cover so many details relevant to the subject. So today's talk is on ancient and medieval Indian contributions, which we normally call classical Indian astronomy, to make it slightly different from what is currently happening in modern astronomy. So the next slide. Next. So here are some references I'm giving from Vedanga Jyotisha. Vedanga Jyotisha is the earliest Indian astronomical text in Sanskrit. So it's customary for us to start talks of this type quoting the following sloka from the Vedanga Jyotisha, which I told you is the most ancient available astronomical text in Sanskrit. There might have been earlier texts also, but they have to be unearthed. The sloka I am quoting here gives you some similes. For those of you who are good in Sanskrit can easily follow. Yatashika mayuranam naganam manayo yata tadvad vedanga shastranam jyotisham murdhanistitam. What it means is, like the crests of on the heads of the peacocks, like the gems on the hoods of cobras, astronomy is at the top of the Vedanga Shastras. There are 6 Vedanga Shastras like Niruktam, Kalpa, etc. Among them, Jyotisha is one. And this text says it is at the top of the Vedanga Shastras. That is the importance given to astronomy in our traditional knowledge system in India. One may wonder why astronomy is given that highest position among the Shastras. The main reason is the Vedic people were more preoccupied with yajnas, yagas, etc. And the prescribed timings are there for the performance of these yajnas and yagas, like Sankrantis, then other important astronomical events. So one should be good at predicting when exactly the equinox takes place, when the Sankrantis take place, etc. So another shloka says, Kalavidana Shastramidam. This astronomy is also called Kalavidana Shastra. Yo Jyotisham Veda Saveda Yajnan. He who knows Jyotisha, he who knows astronomy, also knows the yajnas. He knows when to prescribe the timings of the relevant yajnas and yagas. That is the importance given to astronomy. And to be good at astronomy and to develop astronomy, a deep knowledge of mathematics is a must. So another version of the Vedanga Jyotisha tells us Ganitam Murdhanistitam, that is, mathematics is at the top of the Shastras. It doesn't matter whether you take mathematics or astronomy. In ancient times, they went together, not only in our Indian knowledge system, but even in the ancient Greek and Babylonian systems, mathematics and astronomy have gone on together. Next one. Next. Incidentally, though I am not going very chronologically, I would like to quote the famous Kerala astronomer Nilakanta Somyaji, who composed his text Tantra Sangraha around 1500 CE. He pays rich tribute to his Paramaguru, Parameshwara Acharya. Parameshwara was one of the greatest astronomers from Kerala, and this Nilakanta Somyaji was his grand student, that is student's student. And usually the earlier Western criticism against Indian astronomy was that the ancient Indian astronomers were never good observers. At best, they were mathematical manipulators. But actually, this is a very bad criticism and very much untrue. It was a prejudiced or biased comment or criticism, mainly from the British Indologists. But later on, French Indologists and German Indologists studied our texts very deeply, and themselves they were mathematicians and astronomers. They are all praised for Aryabhata and praised for Brahmagupta and astronomers like that. And they did realize that Indian astronomy was based not only on mathematics, but also on actual observations. I can't go much deeper into these things because this is a spiritual society, and the correct performance of the rituals at the right time is very important to the followers. Otherwise, they would think that they would be incurring sin if they perform at wrong timings. So, prescription of the precise time for every ritual was considered important. And here, after Bhaskaracharya, it is the Kerala astronomers who did a wonderful contribution to the subject to make the predictions of eclipses, etc., as also planetary positions very accurate and precise. This subtle importance of spiritual element is something which Western critics often cannot appreciate or cannot follow. And referring to his Paramaguru, Parameshwaracharya, he says, my Paramaguru Parameshwaracharya devoted 55 long years observing the astronomical phenomena in the sky, and having observed them, critically examining them mathematically, he composed this text called Samadrugganitam. So he says in Sanskrit, Pancha Panchashat Varshakalam Niriksha Grahana Grahayogadishu Pariksha Samadrugganitam Karanam Chakara. Just now what I said. So 55 long years making observations of the phenomena in the sky is a matter of total dedication, and his scientific spirit. And in fact, I told you time restriction is there, I can't go into details. In his commentary, he gives a list of about 15 eclipses, which he actually observed on the banks of the Nila River in Kerala, where he lived. Not only that, in 2 shlokas he mentions that the solar eclipse he predicted did not work out for his place on the banks of the Nila River. Because the eclipses are such, especially solar eclipses, they are visible only in some places, but not in other places. So in his calculations showed that for the latitude of his place, that solar eclipse would not be visible. Then where would it be visible? He found by his calculation that that solar eclipse would be visible for the latitude of the famous Gokarna, the Kshetra in our Karnataka. So it is something interesting that he traveled all the way from his place in Kerala to Gokarna in Karnataka just to observe that solar eclipse. And these days it may be easier to travel, but in the 15th century or 14th century, you imagine the difficulty they had traveling from one place to another by foot or by bullock cart perhaps, sometimes swimming across the rivers. And they were orthodox people who would not eat anywhere, who would not even drink water. So with all these difficulties, if we travel just to observe a solar eclipse, it is something remarkable that speaks of the scientific spirit of our Indian astronomers. It was not just the exclusive case of Parameshwara. All Indian astronomers in the ancient and medieval periods were like that. In Vasishta Siddhanta, supposedly the earliest one among the Panchasiddhantikas, it is said that for determining Tithi, Nakshatra, etc., you must follow that system which corresponds to actual observation. So it is a unacceptable criticism that Indian astronomers were only mathematical manipulators. Of course, we take that phrase as a compliment for the mathematical brains of our people, but it's equally true that they were very good at observation using instruments which were available to them. You may say they were crude instruments compared to modern telescope. Well, that was the situation in Europe also. What sort of instruments did Greek astronomers use, or Babylonian and Egyptian astronomers use? They also use similar instruments. And so, but here the question of accuracy of results was very important. The Indian astronomers did not stick to any particular pattern or particular geometrical model, unlike the Greeks. Greeks were obsessed with the circles and spheres. They thought nature loves symmetry, and the most symmetrical curve in the plane that you can have is circle. And in 3 dimensions, it is sphere. But fortunately, our Indian astronomers did not have such geometrical obsessions, and they had the freedom to think, freedom to modify their models. And because their ultimate aim was accurate results, otherwise their spiritual outcome would not be as expected. This is just by the way of comment on what Nilakanta has said about Parameshwara. For 55 long years, he made observations and wrote his text called Samadrugganitam. So like that, there are many other things. And Parameshwara himself says, Kalantaretu samskaraha chintyatam ganakottamai. He says that whatever procedures and parameters we have given in our text are not permanent. The phenomena in the sky are such, or motions of planets are such, that they need updation. They need revision from time to time. He says, Kalantaretu, in course of time, samskaraha chintyatam, corrections are to be made. By whom? Not by ordinary mortals like us, but by Ganakottamai, by the best of mathematicians. That was the prescription they gave and rigorously followed all along. Next. In our Vedic literature, we have concrete references to Ritus, Varsha, Nakshatras, Dina, equinoxes called Vishuvas, and planets like that. References are there. I have quoted here, and those of you who are interested can copy down later perhaps. I don't go into too many details. For example, they knew exactly when the 2 equinoxes, the vernal equinox and the autumnal equinox, which are called Vishuvas, take place. They are called equinoxes because on those 2 days, world over, the duration of the day and night will be equal. So they had prescribed some yajnas to be performed on these equinoctial days. And solstices, currently on around June 22nd and December 22nd, we have the solstices, winter solstice and the summer solstice. On June 22nd, for us in the northern hemisphere, day is longest and night is shortest. For those who are in the southern hemisphere, it is the other way. These are all recorded, mentioned, and even Vedanga Jyotisha, the earliest text I mentioned, tells you when exactly the solstices take place, when exactly equinoxes take place. So much of astronomical wisdom they had as early as around 1200 BC or so. That is supposed to be the period when Vedanga Jyotisha was currently followed. Later on, of course, revisions were there, planetary motions were studied and all that. So I will come to those things by and by. Next. Seasons, I'm not going into those, but they were familiar with all this. How about the nakshatras? In fact, a unique system in the development of astronomy in India is this nakshatra system. But what they did was they divided the zodiac into 27 divisions. Each is called a nakshatra or asterism. And they used that system to study the motion of the moon. They found that moon takes 27.32 days to complete one revolution, and therefore they divided the zodiac into 27 nakshatras of angular range 13 degrees 20 minutes. That means 360 degrees divided by 27. But actually each nakshatra is a group of stars where the identification is made with a particular star which is most visible in that group. That we call Yogatara, like that Ashwini, Bharani, etc. Not only the Yogataras or individual stars are referred to by the name nakshatra, but also the group of stars in that constellation of angular range 13 degrees 20 minutes is also named after that nakshatra. So they took the number 27 mainly because the sidereal period, that is the time taken by the moon to go around the earth once, is about 27.32 days. What are the nakshatras known to them? Even during the Rigvedic period, they must have known all the 27 nakshatras, but for their yajnas, yagas, etc., and even marriage, some particular nakshatras were considered appropriate. So they named some 4 or 5 or 6 nakshatras like Maga, then Palguni, etc. But in later Veda, Yajurveda, you see a list of all the 27 nakshatras. Sometimes they included the additional nakshatra also and made it to 28. But somehow the 28th nakshatra was dropped later on, mainly because of its high latitude. Because they tried to cover those nakshatras which were closer to the ecliptic, which we call Kranti Vrutta. So like that, but other nakshatras, as I said, only 4 or 5 or 6 are mentioned in the Rigveda. Not that they did not know the other ones, but for their main ritual purposes, these were considered sacred. In fact, one mantra mentions that if a daughter is married away on the Swati Nakshatra day, she will be happy in her husband's house. So that is some such practices they had. That means when Swati Nakshatra means when the moon is in that nakshatra, that is supposed to be auspicious. I don't know why they consider it auspicious. Maybe for some astronomical reason. Next one. Next. Then how about the planets? There are concrete references to 2 planets, Jupiter and Venus. Jupiter is called Brihaspati, while Venus is called Vena. It is a very interesting linguistic coincidence that that planet is called Venus in Greek literature and Vena in Sanskrit. Of course, incidentally, Venus, I think, they consider as feminine gender, whereas Vena is a masculine gender in Sanskrit. Shukra is not a name they have used in earlier Vedic literature. It appears to have come into our literature much later. But these 2 are considered the most important planets because Jupiter is the biggest planet and Venus is the brightest planet, and often it was considered when they are visible, those are blessings from the planets for performing marriage and such auspicious events. Even today, I think that the belief continues. So Guru should be visible, Shukra should also be visible in the sky if the marriage and such events are to be successful and auspicious. Incidentally, the earlier literature, Taittiriya Brahmana refers to an interesting conjunction of Jupiter with Tishya Nakshatra. Tishya is what we call Pushya today, and that is in modern astronomy, it is referred to as Delta Cancri. Delta Cancri is a very important star, and our Rishis in the Vedic times refer to it as Tishya. Today in our Indian astronomy, we call it Pushya. So there is a reference to the conjunction of Jupiter with the Tishya Nakshatra. Historically, it's a very important thing because such a conjunction does not take place frequently. And our scholars in Indian astronomy have estimated that this event must have taken place around 4000 BC. Of course, it's a repetitive or periodic event. So earlier and later also, such an event would have been there. But tentatively, it is estimated that around 4000 BC, this conjunction of Jupiter and Tishya must have taken place. Incidentally, some other astronomical references also in Vedic literature, particularly Rigveda and Yajurveda, point to the period between 4000 BC and 3000 BC. And there is a reference to an eclipse also, supposed to have been worked out or specialized by Atri Maharshi. The Atri family was known to be a scholarly family, experts in astronomy. So there is a reference to that. And a great historian of Indian astronomy, Professor P.C. Sengupta, calculated that that particular solar eclipse was also around 4000 BC. Of course, that does not lead us to the conclusion that all the mantras of Rigveda were composed during that period. It might have been a development over several centuries. But these are some stray incidents, astronomical events, which can be worked out mathematically for their periods. Again, remembering that such occurrences are periodic. They will have taken place earlier also and later also. Next.
Next slide.
Auspicious days for rites and marriage. Stotaram Vipra Sudinatve Hanamya, etc. like that. Yam Kamayeta Duhitaram Priyasyaditi, etc. So that Swati Nakshatra. If a girl is married away in Swati Nakshatra, she would be happy in her husband's house. Some references here, my interest essentially is mentioning about their astronomical knowledge rather than other implications. Mundinda. Next. Now I pass on to the classical period of Indian astronomy. The mathematical planetary astronomy developed in this country some centuries before Aryabhatta. Aryabhatta is the pioneer of mathematical astronomy and even mathematics proper, just as we hold Euclid as the pioneer of geometry in Greek geometry. Not that there were no geometers before Euclid in Greece. We had Pythagoras, we had Apollonius, we had many others, but the credit of systematizing geometry with axioms, theorems and all that, that goes to Euclid. Like that, even before Aryabhatta, planetary astronomy had developed in this country. We have references to Parashara, then Garga, etc. And Varahamihira does mention Garga and Parashara as also some others, including Yavanacharya, by which he means Greek scholar. So they were influenced by some of these imported information or data, as also what is indigenously developed based on mathematical wisdom and their expertise in observations. Now, so far as the texts that are available to us, they almost start with Aryabhatta. His Aryabhattayam is very famous, though it's not a very big text. It is rather cryptic. And in that text, we have both mathematics and astronomy. The later developments in these subjects much depend on or based on Aryabhattayam. He is supposed to have composed another text also called Arya Siddhanta, which is not available to us except by quotations by later astronomers. And his junior contemporary was Varahamihira. In what is typed here, unfortunately, the letter V is missing. Varahamihira composed 3 texts. One is completely astronomical, called Panchasiddhantika, in which he briefly gives the 5 systems of astronomy that were extant during that period, like Vasishtha Siddhanta, Paitama Siddhanta, and all that. But he says among the 5, the best is Surya Siddhanta. That Surya Siddhanta is somewhat different from what is currently popular as Surya Siddhanta. The earlier one, to distinguish, is often referred to as Saura Siddhanta. The currently available popular text is supposed to be a much edited and revised text, and scholars have placed it around 900 or 1000 AD. Now, I mean, earlier also it did exist in some form, but the edited version is of 10th century. But this Varahamihira's text is composed around 505, that Panchasiddhantika. Besides this astronomical text, he has an astronomical text called Brihajjatakam. So entire modern Indian astronomy is virtually based on that text. Of course, there are other traditional texts also, like Brhat Parasharahora, Paladipika, etc. But Varamira's Brhat Jataka is much esteemed. And then he has an encyclopedic text called Brhat Samhita. It is truly a wonderful text where so many Shastras are mentioned, like Aya Shastra, Gaja Shastra, Ratna Shastra, Gemnology, music, cookery, that is Supa Shastra, and so many things are there, and geology, Bhugarbha Shastra. And modern researchers are going into some of them. Of course, not all that Varamira has said is perhaps more scientifically acceptable today, but we can't disrespect their beliefs some 1500 years ago. Those beliefs were there, and even other civilizations had also their own quota of beliefs which are not considered tenable. At the same time, we can't claim that our modern claims will be held valid after another 500 or 1000 years. So such a thing happens in any knowledge system. Then we have a galaxy of Indian astronomers and mathematicians like Bhaskaravan, Brahmagupta and others. Bhaskaravan, there were two Bhaskaracharyas. Bhaskaravan belongs to the 7th century, whereas the more popular Bhaskara, whom we call Bhaskara II, lived in 12th century, and his Leelavati is the most popular text. But coming to Bhaskara I, he was a contemporary of Brahmagupta, and Brahmagupta is held in greatest esteem. It's as a mathematician cum astronomer par excellence. He was really wonderfully great. But unfortunately, there was a controversy between Brahmagupta and Aryabhatta. Of course, they are drawn chronologically away by about 2 centuries. All the same, ideologically, somehow Brahmagupta was opposed to Aryabhatta and goes on criticizing Aryabhatta. But all that criticism is not now acceptable. Aryabhatta was a scientist in his own right, and we do hold Aryabhatta in great esteem. Not only we, even European commentators and critics, Indologists, they have held Aryabhatta as one of the greatest scientists of the world esteem. Now, Bhaskaravan is important for the reason that he is the first advocate of the Aryabhatan system of astronomy. Otherwise, it would have been difficult to follow Aryabhatta just by going by his text because he is too brief. Whereas Bhaskaravan elaborates on what Aryabhatta explains or mentions by the way of mathematics and astronomy. Bhaskaravan composed a commentary on Aryabhatiyam. Unfortunately, it's not complete. Maybe halfway when done, he passed away. But other commentators are there like Someshwara and others. But Bhaskaravan composed two independent texts, which we call Laghu Bhaskariyam and Mahabhaskariyam. In those two texts, Bhaskaravan elaborates on Aryabhatan system of mathematics and astronomy. And in Mahabhaskariyam, he gives beautiful astronomical examples for Diophantine equations, or which we call Varga Prakriti, earlier even Kuttaka. Kuttaka is a Sanskrit word used to refer to the indeterminate equations of the first order. Also, it refers to the procedure because Kuttaka means a pulverizer in English, that is reducing something to pieces. So that is the iterative procedure followed in solving indeterminate equations. And Bhaskaravan is a great contributor and we respect him very much. But of course, the first order indeterminate equations of the type Ax plus By equals C, where A, B, C are given constants and integers, X and Y are unknowns to be solved in positive integers. That we call as Kuttaka. And the contributor of world esteem is Aryabhatta. Aryabhatta is the first mathematician in the history of world mathematics to have given the general method of solving a first order indeterminate equations. Then the more difficult one the second order indeterminate equations, the word indeterminate is used because such equations have multiple solutions. If you take a simple equation, it will have only one solution. If you take a quadratic equation, it will have two solutions. But an indeterminate equation can have infinitely many solutions. Now the question is, how do you get to those solutions in succession? And Aryabhatta gives the method of solving such an equation and finding all the solutions. And Bhaskara elaborates on that. But the more difficult problem of solving a second order indeterminate equation of the type n into x squared plus 1 equals y squared, where n is a positive integer, a non-square number, x and y are two unknowns, and it is a quadratic equation where x occurs in second degree, y also in second degree, and only one equation is given. You have to find values of x and y in integers. It's a very difficult problem. And Brahmagupta of the 7th century gets the credit of giving the general solution of such an equation for the first time again in the history of world mathematics. We are indeed proud of our ancients so far as the development of mathematics is concerned, so also its application to astronomy. And then there are others into whom I don't go. For example, Vateshwara was there, Manjulacharya, Aryabhatta II. But Manjulacharya gets some credit, extra credit. He composed this text called Lagumanasam in 932 AD. But what is the importance of this text? It is a brief text which we call Karana Grantha. In the chapter on eclipses, he mentions that to get the accurate timings of the circumstances of the eclipse, namely the sparsha and moksha, we have to get the instantaneous angular velocity of the moon. Otherwise, the practice world over was to take the average angular velocity of the moon, which is about 13 degrees 10 minutes, 790 minutes of angle. But this Manjula for the first time tells us that that is average velocity, but we have to take the daily true motion. Today's rate of motion of the moon in the morning is not the same as in the evening, and it will be different tomorrow morning. It is like the British weather, which goes on changing from morning to night. And this is really remarkable scientifically speaking, not only conceptually, but mathematically. He says in that process, the trigonometric ratio sine ja becomes cosine cotija. Today we know that the differential of sine theta is cos theta d theta. This Manjula could intuit as early as 10th century. It's a very important kind of calculus concept, and we have to give credit to Manjula for that. Not only that, I'll refer to these calculus concepts a bit later. And then we had Aryabhatta II is not that important. He composed a text called Mahasiddhanta. Next. Then we had Bhaskara II, the second Bhaskaracharya, who was born in 1114 AD. Just a few years back, 6 years back, we celebrated the 9th birth centenary of Bhaskaracharya. Not only in India, but even outside India, scholars who have been working in this field, they also celebrated Bhaskaracharya's 9th centenary. And Bhaskara II is considered the most popular author in our field, mainly because he was not only a mathematician and astronomer, he was a good poet also. And his language is so simple and beautiful chandas he uses in his texts. He composed 3 important texts, 3 or 4. Siddhanta Shiromani is his magnum opus, a voluminous treatise on astronomy. Then Karana Kutuhalam is a Karana Grantha, and personally permit me if I mention that I translated along with my research associate this Karana Kutuhalam into English, and it is published by Indian National Science Academy, Delhi, INSA. So Siddhanta Shiromani and Karana Kutuhalam are his 2 astronomical texts. And two mathematical texts also he composed. One is Bijaganitam on advanced algebra. In Lilavati also algebra is there, but it is elementary, like quadratic equations and all that. Whereas in Bijaganitam, more advanced mathematics like Kuttaka, Varga Prakriti. Varga Prakriti means solving a second order indeterminate equations. The original contributor was Brahmagupta, but Brahmagupta's procedure was simplified by Bhaskara by what is called Chakravala method. Chakravala is cyclic method or iterative procedure. So he simplified the whole thing. That is all detailed in Bijaganitam. And a very interesting historical anecdote I can mention. There was a famous European mathematician, French mathematician by name Fermat. Fermat is famous both in physics and mathematics. Often physicists pronounce his name as Fermat, but T is silent there, being a French name. Fermat. He was a great number theorist and also good in experimental physics. But by profession, he was not a mathematician. He was an amateur mathematician, but his contribution is remarkable. In the 16th century, he threw a challenge to his fellow mathematicians in Europe to solve an equation like 61 into x squared plus 1 equals y squared. 61 is a constant which we normally denote by n, capital N. X and y are unknowns. You have to find integral values for x and y satisfying that equation 61 into x squared plus 1 equals y squared. Believe it or not, none of the European mathematicians, including the top number theorist Fermat himself, could ever solve that. Not only solving the equation, they could not even guess a single solution. Of course, trivial solution is there, x equals 0, y equals 1. But you want non-trivial solutions. None of them could do that, though during that period, especially in France and Germany, there were very brilliant mathematicians. But 500 years earlier to this Fermat, in our own country, we had this Bhaskara too, who has solved that very same problem, 61 into x squared plus 1 equals y squared, just as an example in his Bijaganitam. That example is not any sacred by itself, but he gives that as an example. He gives another example, 67 into x squared plus 1 equals y squared. And not only that, he explains how any such equation can be solved. And mind you, even the least solution of that 61 x squared plus 1 equals y squared, among the non-trivial solutions, the least one has 9 digits for x and 10 digits for y. So the least values are that big. Remember, we have to be amazed at their way of calculations and numerical computation when calculators were not there and modern writing materials were not there. How were they calculating such huge numbers? Not only that, using those 9-digit and 10-digit big numbers, you can generate the further solutions of that equation having 30, 40, 50 digits. That is Indian mathematics. That is the brain of our ancients. So that is Bhaskara too. Of course, his Lilavati is a very popular text, but comparatively it's an elementary text where arithmetic and algebra and a bit of geometry, Kshetra Ganita as they called it, areas, volumes, etc. were discussed. Then we pass on to the Kerala astronomers. And after Bhaskara, what happened? Bhaskara was in the 12th century. The general belief was that after Bhaskara too, there was no development of mathematics or astronomy in India at all. Historically, partly it is true, because foreign invasions were there, succession of unwanted invasions, destroying of libraries, destroying of our temples, all these things happened, and no cultural development was possible in northern India. But luckily, in the remote corner of South India, remarkable development took place in the fields of mathematics and astronomy almost exclusively due to these Kerala mathematicians. It starts with Madhava. Madhava was one of the earliest among the Kerala astronomers. He belonged to the 13th, 14th century. He remarkably, he is supposed to have given infinite series expansions for sin x, cos x, pi by 4, etc. And in modern mathematics, in the field of calculus, we have these results only after Newton. Newton and Leibniz are supposed to have invented calculus in the 17th century. So after 17th century, the followers of Newton have given us following Taylor series, Maclaurin series, etc. We have infinite series expansion for sin x, cos x, tan inverse x, pi by 4, etc. That pi by 4 series comes from the expansion of tan inverse x given by Gregory, James Gregory, I think. But that same pi by 4 series was given by Madhava as also for sin x in the 13th, 14th century period. How could they give all these things before calculus was invented? That is something remarkable. Here comes the intuitive brain of these people, and purely by geometrical and algebraic methods, they have given the series expansions. It is something remarkable. And not going into details because it may appear too technical. But then after Madhava, we had Parameshwara, Nilakanta Somyaji and all these people. Parameshwara was more an astronomer, and I referred to him earlier, how much of scientific spirit he had. He has composed many small texts on eclipses and other things. But Nilakanta Somyaji is perhaps the best among them. He was a prolific writer, and his Tantra Sangraha, a huge text, is the magnum opus of Nilakanta Somyaji. He has also composed a commentary on Aryabhatiyam, which is called Aryabhatiya Bhashya. And historically, what is important is the heliocentric model. We give credit for that to Copernicus. Yes, Copernicus did give this heliocentric model. Until then, world over, the geocentric model of planetary motion was followed, whether in Greek astronomy or Indian astronomy or Chinese astronomy like that. But Copernicus is given credit for his heliocentric model. But the problem is, actually, this Copernican model did not work out well. Though conceptually he was correct, mathematically he was not. When he transformed the coordinate system, he should have adequately done it mathematically, which he did not. Nor could he foresee the possibility of planets moving in elliptical orbits. It is something amazing and almost tragic that the ancient Greek thinkers and astronomers could ever imagine that planets might be moving in elliptical orbits. They were so much obsessed with circles. So they were forced to have circles, small circles, big circles, epicycles and all that. And unfortunately, even Copernicus sticks to that epicyclic theory. Though his heliocentric model is correct, that is, planets move around the sun and not around the earth. That part is correct. But that the planets move only in circles, again, is not mathematically correct or physically correct. The credit goes only to Kepler for giving us the three famous laws of planetary motion, including the first one, which says that planets move around the sun. Earth also is a planet. Of course, Copernicus did recognize that Earth also is a planet, but it was given to Kepler to declare that the planets do not move in circles, but in elliptical orbits. How about Nilakanta Somyaji? How about the situation in Indian astronomy? I am proud to tell you that Nilakanta Somyaji, in his Tantra Sangraha, gives something similar to heliocentric model. We call it today quasi-heliocentric model because his system was that the planets go around the sun and the sun himself with his family of planets appears to go around the earth once a year. Mathematically, this is not wrong. Even though today we know that the earth goes around the sun once a year, by relative motion, you are not wrong to recognize sun's motion around the earth in the course of a year. But what is important is this Nilakanta does recognize that the planets go around the sun. That is one thing. Another thing is coming to ellipse. It is true that our people did not recognize that the planets move around the around the sun in elliptical orbits. But their model of heliocentric motion, their model of epicyclic theory is something superior to the Ptolemaic theory. Ptolemy did give the epicyclic theory and Copernicus improved upon that, all that is true. But Indian epicyclic theory is somewhat different. Here, I don't go into details. The so-called epicycles, two of them are recognized, called Mandavritta and Shigravritta. And the greatness of Indian system is that for any given heavenly body, including the sun, the moon, and the planets, there is a epicycle, two epicycles for planets, and only one epicycle for the sun, and one epicycle for the moon, called Mandavritta. But what is important is, these people recognize that the radii or circumferences or peripheries of these epicycles, they are not constants. They are variable. They are pulsating. So they become increased, they become decreased like that. And that is really a model which works better than the Ptolemaic model or even Copernican model. And even to this day, most of our astronomical results, according to traditional procedures, work out reasonably well, except that the parameters have to be slightly updated. So that apart, and not only that, coming to the model, it's interesting that Tycho Brahe, one of the greatest European astronomers and guru of Kepler, was not ready to accept, in fact, he rejected outright Copernican model. Copernicus came earlier than Tycho Brahe and he propounded his heliocentric model. But very interestingly and strangely, this Tycho Brahe rejected that Copernican model outright. Why did he do that? Because he found that in reality, Copernican model would not work well. Mathematically, he was not correct. That was because of a silent loyalty Copernicus perhaps had towards Ptolemy. That was a mistake. In science, we should not be too loyal to our predecessors. We must be bold to question them. And this statement is made by Bhaskaracharya himself. He says that we can't accept the ancient statements per se or in toto. We have to question them, and only when they are acceptable logically, scientifically, and by observation, we have to accept. Even Adi Shankara mentions that in his commentary on the Bhagavad Gita. He says, even if 100 Shrutis, Nahi Shruti Shatamapi, even if 100 Shrutis declare that fire is cold or does not emit light, it's not acceptable. Such Shrutis will not be pramanyam na upaiti. So it is very important how our ancients had that bold spirit of logical thinking that we have to highlight to our present generation of students. So they were not taking tradition blindly. That's how were born Jainism, Buddhism, and so many things. Charvakas were there. Whether we accept them or not today is a different thing. But they dare question the ancient findings or experiences. So Ptolemy somehow was the, what shall I say, emotional guru of this Copernicus. So he dared not question Ptolemy so much. Otherwise, he would have been a better scientist and better model he could have pronounced. There we give credit to Nilakanta, who says this model of planets going around the sun and the sun apparently going around the earth once a year is a model known to my Paramaguru also. He gives credit to his Paramaguru Parameshwar of the 13th century. And he questions this Nilakanta question, why did it not occur to our ancients? Such a simple model is something remarkable. Nilakanta giving this model when physics was not so much developed here, no mechanics was developed, only by kinematic considerations and their intuition and experience of observations, they pronounced these statements. Then we have Ganesha Devajna. Of course, I'm going one by one, but I mention the important ones because time restriction is there. Ganesha Devajna was a Maharashtrian astronomer who practiced his profession in Kashi. Many of these Maharashtrian astronomers referred to as Devajnas, Krishna Devajna, and like that who came after Bhaskara. So they were in the 13th, 14th, 15th, 16th centuries. Many of them migrated to Varanasi and practiced there. That was because Varanasi was the most important center of learning. They got patronage and recognition in Varanasi. Not only that, exchange of ideas with North Indian scholars was also possible in a place like Kashi. And he composed a text called Grahalagavam. This Grahalagavam is the most popular astronomical text all over India among the Panchanga makers and practitioners of traditional Indian astronomy. Why is it popular? It's a very important thing historically. Astronomy, as is known to the practitioners mathematically, is totally dependent on spherical trigonometry. You must use sine, cosine, and all those things. And spherical trigonometry is rather complicated. And the Panchanga makers, traditional Panchanga makers, it was a family profession. Not all of them were necessarily good mathematicians. So they had difficulty in finding, say, sine or cosine of 22 degrees or 23 and a half degrees, like that, because there were no calculators. They used tables, but interpolation is necessary if you want to find the trigonometric ratio of an angle between two entries. Now this Grahalagavam author, Ganesha Devajna, simplified the whole of Indian astronomy. What did he do? He completely dispensed with sine and cosine. So how did he dispense with? How can it be possible to get rid of sine and cosine and yet have accurate astronomy? It was possible. He replaced the sine function by an algebraic approximation. It's a very good approximation, but actually given out not by Ganesha Devajna, but by Bhaskara I. Bhaskara I in the 7th century was the first mathematician in the world to have given such a good approximation for the trigonometric function sine. It's an algebraic expression which was easy for our Panchanga makers to calculate. And mind you, the formula gives correct values of sine even up to 3 decimal places for any large angle. Our modern students of science and engineering know that when you study the mechanical problem of a simple pendulum is called simple because in getting the solution, you remember the formula for the period of a pendulum, T equals 2 pi into root L by G. So where the small g is the acceleration due to gravity, L is the length of the pendulum and all that. But how do we arrive at that? By solving a first order differential equation. How do we get the first order differential equation? By using an approximation for the sine function. When theta is small and in radians, we know that sine theta is approximately theta. That approximation is used to reduce this pendulum problem to a simple pendulum problem of first order differential equation. Otherwise, it results in a nonlinear differential equation. So, but compared to the modern approximation we make, Bhaskara I's approximation is far superior. The sine theta approximately equal to theta is good enough. Only if theta is very small, and our physics teachers don't generally tell the students how small the theta should be. Amplitude of a pendulum, whether I should take 2 degrees, 3 degrees, 10 degrees. You can't easily take 2 degrees or 3 degrees If you take 10 or 15 or 20, it ceases to be a simple pendulum and the answer will not be correct. But the approximation given by Bhaskaravan is an extremely good one. As I mentioned, the angle can be as large as you like, and accuracy is up to third decimal place, which is good enough for our calculation. And it is this Ganesh Devajna who took the maximum advantage of that formula given by Bhaskaravan. Entire astronomy was simplified by getting rid of sine and cosine. That credit goes to Gralagam. And throughout India today, among the traditional Panchanga makers, this Gralagam is popular. And I may humbly point out that I and my co-author have the credit of translating this Grahalagam to English, and it is published again by Indian National Science Academy, INSA in Delhi. And today it's a popular text, but not copies are easily available. Then we have the other great Kerala astronomer, Jeshtadeva. He is famous for his Yukti Bhasha. Yukti means rationale or logic. Bhasha word is used to mean that it was composed in Malayalam language and not Sanskrit. The usual practice was to compose these texts in Sanskrit, the advantage being that it can be understood all over the country. If I compose a text in Malayalam, only Kerala people can read it. If I compose in Kannada, only Karnataka people can read. But if it is in Sanskrit, that was the national language used for literary compositions. Throughout the country, it can be followed. Similar practice has been there in Europe also. Though Newton was an Englishman, his Principia Mathematica is in Latin. Though Copernicus' mother tongue was not Latin, he composed his De Revolutionibus, the astronomical text, again in Latin. So Latin was the literary language followed over Europe, all the countries there. So also here in India, it was Sanskrit. But sometimes they preferred the local language, and especially in Kerala, we have a few texts which are in Malayalam. But that Malayalam itself is much Sanskritized. So Sanskrit, Malayalam, they mix like that. Yukti Bhasha is a very great text in which rationales or proofs are provided for important mathematics and astronomy results. Then we have the famous Orissa mathematician and astronomer, mainly astronomer, Chandrasekhara Samanta. Chandrasekhara Samanta is considered as the last among the traditional astronomers, or whom we call barefoot astronomers. He was from Orissa and he has composed a voluminous Sanskrit text called Siddhanta Darpana. And very interestingly, the results obtained from his text are very close to modern values. In fact, he was not modern educated at all. Maybe he had not even seen a telescope, though he was in the 19th century. But his text is really great, and we are popularizing Siddhanta Darpana. He wrote the text in Sanskrit, but the manuscript was in the local script, Udiya. And now it is rendered into Devanagari script, and Hindi and English translations are available. Then we have other mathematicians. Among them, the most, popular and useful author was Venkatesh Ketkar. Venkatesh Ketkar was a Maharashtrian astronomer who worked from Bagalkot. Today Bagalkot is in our Karnataka. And Ketkar did a wonderful thing. What he did was, he found that the traditional texts in astronomy were to be revised because the planets do not obey our text. Their parameters go on changing from century to century. So he felt it should be modernized. So this Venkatesh Ketkar used the modern formulae for the computations of phenomena and planetary positions based on Leverrier, Brown, Newcomb, American astronomer, and all such contemporary authors of his time. He used their formulae, but the wonderful thing he did was, he put all those formulae in the traditional Siddhantic format. He wrote the text in Sanskrit called Ketaki Grahaganitam and another Jyotir Ganitam. Both are in Sanskrit, both are in shloka form, and which Panchanga, traditional Panchanga makers could easily follow. So today in India we have many Durganita Panchanga Kartas who use this Ketkar's work. But of course, again, Panchanga making is a big story by itself. How far they are reliable, how far they can be trusted, etc. questions arise. I'm not going into that. But Ketkar did yeoman service to this field by rendering modern procedures into the Siddhantic format, which our traditional Panchanga makers could easily follow. Sir Mundaki.
Next.
No, I'm not going into too many details because they are more computational. Civil days, they had in this time analysis were the long periods called Mahayugas, Kalpas and all that. Mathematically, what was the need for that? The need mathematically is greater accuracy is there. For example, when you want to calculate daily rate of motion, they give in terms of number of revolutions of each heavenly body in the course of a Mahayuga or a Kalpa. When the denominator is large, the advantage is that in the numerator, even in the final digits, if there is even if there is a small error, it does not contribute to the error in daily computation, and the percentage of error will be small. So that is the mathematical advantage of these huge numbers, though the inspiration came from Puranas, where they speak of Kalpas, Yugas and all that. But mathematically, for computations, it is useful. And in this table, I have provided the number of civil days in the course of a Mahayuga. It is really significant how they could arrive at such accurate values. You will see that there is steady improvement in the values they have given chronologically based on observations. The next one.
Next slide.
Here you see I have given the number of revolutions of each heavenly body in the period of a Mahayuga. Mahayuga means 432 into 10 to the power of 4 years, that is 43 lakh 20,000 years. 1/10 of that is Kali Yuga, that is 4 lakh 32,000 years. Now 1000 Mahayugas will make a Kalpa, that is 432 into 10 to the power of 7. That will be a Kalpa. If you give the revolutions in a big period called Kalpa, the accuracy will be greater because in the last digits, well, they matter. But here generally it is given for a Mahayuga. Of course, this Yuga theory traditionally is one thing, but Aryabhatta revised. He gave his own Yuga theory. What he did was, the so-called Mahayuga, he called it Yuga only. Again comprising 432 into 10 to the power of 4. That is 43 lakh 20,000 solar years. But he called it only Yuga and not Mahayuga. And he did not divide them into Kruta Yuga, Treta Yuga, etc. What he did was, he divided that period into 4 equal periods and called them Yugapada. So that was the mathematically again useful, because we found that among the numbers of revolutions of planets, 4 was a common factor. So calculations can be simplified instead of doing this Kali, Dwapara, etc. The next one. Here you see I have given the table in which daily rates of motion of the bodies are given, and you can compare. I have compared the values of Surya Siddhanta, Siddhanta, Shiromani of Bhaskara, then Kandakadhyaka is a Karna text or handbook of Brahmagupta, and finally, according to modern astronomy. You see how interesting, remarkable coincidence is there among the traditional values and the modern values. That's why even according to our traditional text, today's prediction of eclipses and planetary positions are reasonably correct. The next one. I'm not going into details. I have explained the theory of epicycles as followed by Indian astronomers. And what is remarkable is their computations make their epicyclic model almost close to elliptical orbits, elliptical, what shall I say, model. And I told you the reason also. They gave this so-called epicycle, the small cycle shown there is an epicycle. Like that, one more epicycle is there for planets. It's called Shigravritta. And the radii are prescribed. And I told you they are variables, unlike the Ptolemaic system in which they are constant. This variable periphery of the epicycles of the planets result in almost approximate elliptical orbits. So without knowing that they are elliptical, our people gave the values in such a way that these loci of the planets approximate an ellipse. The next one. Those are mathematical details which we have shown in our books and also in our research papers. I am not going into details to prove how the orbit is elliptical. Next. So,
Next.
So these are all details. What I said, periphery or radii. If you divide the circumference by 2 pi, you will get the radius. So the variable radii you can see according to Aryabhatiya. Of course, Brahmagupta's text Kandaka Deka is an elementary text. There, because approximations are intended, he gives constant values. But then Surya Siddhanta also gives variable peripheries for the epicycles. These are for Manda epicycles. Incidentally, the Manda correction corresponds to what we call the equation of the center in modern astronomy. The modern procedure is to use the equation of center, first to find the mean position of the planet, then apply the equation of the center, because the orbits are not circular, they are elliptical. Then all these give you true heliocentric positions, that is with the sun as the center. Those you have to convert into geocentric coordinates by transformation, and that corresponds to what we call Shigra Samskara in our Shigrapala or Shigra Samskara in Indian astronomy. Again, without knowing about the heliocentric model, it is remarkable that Indian astronomers gave out what they call the Shigra Samskara, and trigonometrically that formula is very much close to modern transformation formula from heliocentric to geocentric. It's really remarkable without being conscious that the orbits are elliptical. I'm sorry, they are converting from heliocentric to geocentric. Next one. So similarly, what I call Shigra epicycle, that is corresponding to transformation from heliocentric to geocentric. There also they have given the peripheries which are based on the distances of the planets from the Earth. No, sorry, the astronomical, in terms of astronomical units, the heliocentric distances, that is from the sun. And if you extrapolate to modern astronomy or procedures, what they are, I have given in the final column. And we see that our Indian values in most of the cases are close to what would have been in modern astronomy if the epicyclic theory was adopted. Next one. Retrograde motion of planets. It's an interesting phenomenon that planets move in the eastern direction as we observe from the Earth. But each planet, I mean planet, not sun and moon, each planet after some time appears to move backwards. That backward motion is called retrograde motion. We call it Vakragati in our traditional astronomy. And those of you who have seen horoscopes of individuals, you'll see in some cases the planets are mentioned as Vakrashani, Vakraguru, or they abbreviate it as Vaguru, Vashani, like that. There, of course, astrologers may tell you that Vakra planets are strong and things like that. For astronomy, let us forget it. So Vakra means they appear to move backwards. That is, instead of moving eastward, they appear to move westward. That is for a certain period. Then again they change over to the usual course. So that is, those points are called critical points, where at a certain angle, the planet appears to change from eastern motion to western. And again another point where it changes from again west to east. In mathematical language, we call them critical points or the stationary points. And it is very important to notice that today we can get to those critical points using calculus. We know that when a function attains its extremal value, maximum or minimum, the derivative is 0. dy by dx equals 0. Or in mechanics, ds by dt or d theta by dt, angular velocity is 0. And some glimpses of calculus we see in the astronomical texts of Manjulacharya of the 10th century I mentioned earlier. And in Bhaskara's Siddhanta Shiromani, also we see that he explicitly mentions that at the extremal point, the rate of change of motion vanishes. That is what we today call dy by dx equals 0 at a maximal or minimal point. Using that concept, the critical points of planetary motion are given by Bhaskara and also by earlier mathematicians, and I have listed them here. And you will see that the Indian values given by Bhaskara, Lalla, Surya Siddhanta, and Brahmagupta are close to what we get in modern astronomy given in the first column against the planets. It's remarkable. Before calculus was formally invented by Newton and Leibniz, how could these people get such accurate values? Even today they are valid. Okay, the next one. So eclipses, they form an important phenomenon in our in astronomy. In the sky, everybody has watched a lunar eclipse or solar eclipse. It's a very spectacular sight. And astronomers in India, even very ancient among them, they had known the cause of eclipses. They knew that eclipses are not caused by any demon like Rahu or Ketu swallowing the full moon or the sun. They knew that eclipses happen only on Amavasya and Purnima, that too not on all of Amasyas or Purnimas. That is because the lunar orbit is inclined to the ecliptic at an angle of about 5 degrees. If all the three, Earth, Moon and Sun, if they were coplanar, then every Amasya there would have been a solar eclipse, and every full moon day there would have been a lunar eclipse. That does not happen because the plane of lunar orbit is inclined to the plane of the ecliptic. Ecliptic is the apparent path of the sun as observed from the Earth. So they knew this, and they knew mathematically how to predict eclipses very accurately using all the needed parameters like the angular diameters of the sun, the moon, Earth's shadow. They knew the geometry of eclipse. They knew that lunar eclipse is caused by Earth's shadow cone. They knew that the solar eclipse is caused by the moon covering the sun. So in their own language, they do mention, for example, Bhuchayam Swagrahane Bhaskaram Arkagrahe Pravishati Induhu. At a lunar eclipse, the moon enters the shadow of the Earth, and at a solar eclipse, the moon covers the sun's disk. So like that. And how about predicting eclipses by Shakunas? Among common people, there were some beliefs. Even today, many people may believe, like dropping an oil in water and knowing the shape or something of the oil drop in the water. It seems it is believed they can predict about the eclipse and all that. And there was also a belief that preceding an eclipse, there are earthquakes But today we know that earthquakes have nothing to do with eclipses. And this was known to Varamira and Aryabhata. So they say, Evam Uparaga Karana Muktamidam Divyadruk, I can't read it, Acharyahi. So Acharyas knew the scientific cause of eclipses. It is a shadow play. They knew that the demons of Rahu, etc., don't swallow the moon or the sun. And the belief that earthquake, etc., happens before eclipses is also not true. Anyasminnapi kale Bhavan Keva, etc. That is, at other times also, earthquakes take place. In fact, at every given moment, I think in some part of the world or the other, earthquake will be there, but no eclipse happens like that. For eclipse calculation, separate geometry is necessary, and we know the parameters which are responsible. Incidentally, I may mention that there is a famous catalogue in Sanskrit by one Thakura of the 14th century, I think, 14th or 15th, in which you see he has tabulated eclipses, future eclipses for about thousands of years, up to 27th century. We are now in the 28th century, no 21st century we have entered. So up to 27th century, he catalogs solar and lunar eclipses for thousands of years. He gives the traditional dates of this lunar month, then solar date and nakshatra of the moon and so many details. And we have checked up that they are all correct. And it's wonderful and that has to be popularized. Of course, we have the famous German tables or catalog called Opolzers. But coming to India, it is remarkable. And the story goes that the author Hemangada Thakura composed this text sitting in the jail. It seems he was jailed by Akbar. Akbar was the monarch then, and this Thakura was a petty palegar or something like that, and he failed to pay the tax to the emperor, and therefore he was jailed. So sitting in the jail, it seems, he composed this table of so many thousands of eclipses. So it is a remarkable brain and mind. Even if the story is not true, we don't know really. It is remarkable that one could form the catalog of thousands of eclipses like that, and they are very accurate. We have checked up. So like that, eclipses are analyzed, and our Indian astronomers were experts in predicting eclipses.
So, Dr. Balachandra ji, I wanted to remind you about the time as well. So, we are running short of time. Yeah. So, do you want to conclude on this topic of Varamira? Yeah, please go ahead.
So one could go on like that, and astronomical tables are there, the saranis they are called, and today for Panchanga making and yeah, it can go on.
Next slide.
Panchanga making and observations, they use the saranis. Similarly, in Kerala, they have the Vakya system, which is a very remarkable system in which Sanskrit sentences are there, and each sentence is meaningful also. You can say Ramaya Namaha or Krishnaya Namaha, but each letter there represents a number following what is called the Katapayadi system. Those of you who are experts in Carnatic music are well aware of the Katapayadi system. You have Dhira Shankarabharana and all that. That Dhira represents 2 digits, which corresponds to the one of the 72 Melakarta ragas, like that. Here in astronomy, these planetary true positions, the final positions, are given in Vakyas, which are easy to memorize, easy to read and even understand. And those are not arbitrary sentences. They have other meaning also, but meaning is not relevant to us because we are interested in the values. And Vakya system is a very remarkable contribution of the Kerala astronomers. So in Tamil Nadu and Kerala, generally, even today, they do use the Vakya system. Like that, other tables, saranis are available. based on Surya Siddhanta and other. Not only in Sanskrit, they are available in Telugu. In fact, we are using one or two such Telugu scripted tables in Kannada script like that. So I'm not going into maybe another lecture on tables. Makaranda Sarini is a very popular astronomical tables where you see it is based on Surya Siddhanta, especially in northern India. That Makaranda Sarini is very famous, and our research team in Bangalore is ardently working on Makaranda Sarini, as also other tables. Particularly, one of them is in Telugu script. Fortunately, the numerals are the same in Telugu and Kannada script, except 3 and 7. 3 is like modern 3. 7 I get confused. So what confuses me, I take as 7 while reading the script. I mean, because we know the way the planets move and all that, such doubts do not arise. Even if some print mistakes are there, we can rectify them. And we may publish the Telugu scripted table shortly if some publisher obliges us. The difficulty is the popular publishers don't take up such works at all. So our Vedavyas Institute can perhaps support us. So, okay, I think I should conclude. Thank you very much for listening to me all this time. Our field is so vast. Thank you very much.
No, it is really great talk, sir. And I know it is highly technical and also very energetic to hear from you on the contributions of the Indian astronomers and to the subject of astronomy. I had a couple of questions from my end as well before I take up some questions from the viewers. So one question I had is about the dropping of Abhijit Nakshatra. You did mention out of the 28 nakshatras that Abhijit was dropped at a later point of time, and you did talk about it briefly about of its high altitude or latitude, sorry, high latitude, that it has been removed. So any specific reason or technical or scientific in nature of suddenly Abhijit becoming of higher latitude, or was it from beginning higher latitude, or what was the reason, sir? Any
No. I didn't go into details. In fact, we have been working on this Abhijit Nakshatra as also Agastya, their heliacal rising and things like that. Some stars, they become circumpolar. There it is not the latitude. Latitude is fixed. But the declination is the perpendicular distance to the celestial equator. That goes on changing. And every star at some stage attains a very large declination. Then it is likely to become a polar star. For example, Agastya and Abhijit both became polar star, almost polar stars during 12th century BC or so, as per our computations. Abhijit became the north circumpolar star, and that means the Earth's axis almost passes through that star in the northern direction. And this Agastya is a southern star, so it became the almost south polar star. So maybe that is the reason. It's not the altitude or latitude. Latitude is fixed, but the latitude is large, both for Agastya and Abhijit. That is one thing. But maybe declination-wise, it had a fall. That means declination-wise went on decreasing. In fact, in our Vedic literature, some stories are there that there was a competition between Abhijit and I think Rohini and things like that. There are allegorical stories which have astronomical significance, and we have to go into details. But the type of work I have been doing is more computational. So anyway, Professor Abhyankar of Hyderabad, he was in Usmania University. He was a great astronomer, and he has written wonderful books on galaxies and all that. He went rather deep into the allegorical references to astronomical events in our Vedic literature. That deserves a deeper study. But my concentration, as I said, is more computational. And of course, we have been working on Agastya as well as Abhijit. So Abhijit, in course of time, was not among the nakshatras considered, though earlier it was there. in earlier Vedic literature and Aranyakas, Taittiriya Aranyaka, Shatapatha Brahmana, and in such texts, references are there.
Sure, sir. And one more question from my end was about the combination which you mentioned of Jupiter with the Tishya or the Pushya Nakshatra, right? So, as we understand today, Pushya is one of the 27 asterism or the nakshatras, and Jupiter goes around the zodiac in 12 years, once in 12 years, right? So, why is that if this event or a
Once
combination
in 12
happens?
years, it should happen.
Yes, once in 12 years it should happen. Then what is this greater significance about this you mentioned in the Aitareya Brahmana? Is there any special relevance? Or Taittiriya
Yeah.
Brahmana, I think.
No, Aitareya Brahmana, that period has to be estimated. The Taittiriya Brahmana. But your question is relevant. That, as you said, Jupiter goes around the sun once in 12 years. So every 12 years, it should be near the Pushya Nakshatra.
Correct.
Here, by conjunction, there is a difference between the concept of conjunction in astrology and astronomy. I did study astrology once. So if two bodies are in the same Rashi, they would say it is conjunction normally in astrology. But in astronomy, we don't take it that way. It should be close conjunction. Close conjunction means the difference in latitudes of the two bodies. Every star has longitude and latitude. Every planet also has that. The only difference is the latitude of the planet goes on changing, whereas the latitude of a star is almost fixed. Now, if there should be a deep conjunction, sometimes even resulting in occultation, the difference in their latitude should be very small. It is like an eclipse, like solar eclipse. Here also, one body covers the other. So perhaps they meant a close conjunction and not the periodic conjunction of 12 years.
12 years. Okay, great, sir. Thank you for clarifying that. So, do we have any other questions? I don't see. I think so. That's all, I think, sir. With this, we will conclude the session. On behalf of International Institute of Vedic Sciences, IIVS Rishi Vatika, thanks to Dr. Balakrishna ji for his great talk on the Indian classical astronomy, and it was indeed enlightening to learn about Indian astronomers and their contributions. Thank you very much, sir. We would also like to thank all the viewers who have joined us live on Rishi Vatika YouTube channel and request all to subscribe to the channel for the latest notifications of the future talks. Hari Om Tat Sat.